Hello, my name is Manuel Helbig, and it is a pleasure today to give the first talk for the virtual Ameriflux DOE workshop. And my talk will address how we can use continuous atmospheric boundary layer measurements at surface flux tower sites to really advance our understanding of land-atmosphere interactions. I would like to start the talk with a quick introduction to the Ameriflux network. So the Ameriflux network is a network of observation sites where we measure ecosystem CO2, water, and energy fluxes, and we're using the eddy covariance technique to measure turbulent fluxes. And here you see two conceptual diagrams, how we measure evapotranspiration, so the water vapor flux, and the net CO2 flux, which is that net ecosystem CO2 exchange. So usually you will find a tower with a eddy covariance system situated well above the canopy. You have a profile of measurements of humidity, air temperature, CO2 concentrations that would give you an idea about the storage changes below the measurement height. And then we measure here with a sonic anemometer, we measure wind velocities, and then a gas analyzer for water vapor and CO2 concentrations. And then we measure this at 10 Hertz frequency to really capture the turbulent motions. And then here you see the turbulent motions, the eddies, that would, when they pick up air close to the canopy, where we have a source of water vapor because of transpiration during the day, so there will be higher concentration of water vapor. And then when air is picked up here and transported with an updraft past this sensor here, we will see a positive vertical wind velocity, but also a short increase in the water vapor concentrations. Now, when there is a downdraft, we go from a region of low concentration to a region of high concentration, so we would see a negative vertical wind velocity with a short decrease in the water vapor concentration. And then use the covariance for about like half an hour averages to get net water vapor flux. And the same you can do for CO2 to measure the net CO2 exchange. And again here it's inverse because there's a sink of CO2 in the canopy during the day because of photosynthesis. So whenever air is picked up here where concentrations are lower and transported into the atmosphere with an updraft, you would see a decrease in CO2 concentrations. And then with a downdraft, you would see the opposite. You would see a short increase in CO2 concentrations. So these kind of measurements are conducted all across the Americas. You can see here the distribution of the Ameriflux sites, and they're highly biased towards the US and southern Canada. But there are sites also at high latitudes. There have been sites added in northern Canada. There are sites in Mexico, Central America, and South America. So we really cover a wide range of ecosystems all across the Americas. And it's not only an American network. There are other sites all across the world. So if you look here at the map of both currently active and also legacy site, you see like a huge number of sites in Europe. And there's, for example, the integrated cardinal observation system, which is running flux tower sites all across Europe. There is Aerosol with flux towers all across Asia, and Ausflux with Australian and New Zealand flux tower sites. But there are also sites in Africa, and some of them originate back to a project called Carbor Africa, but also more recent flux towers that have been added in Africa. So if you think about the Ameriflux, it's really important to know that this is a network that is managed by principal investigators that run towers, and they're contributing their data to share with the community. And if you look at the funding structure compared to other different networks of observation networks, you see here the National Ecological Observatory Network, the Long-Term Ecological Research Network, and the Critical Zone Observatory, and they're all funded by NSF. And as you see there to the left here, there's a high degree of centralization. For example, NEON uses the same instrument, same processing, same calibration all across all their sites. But then if you look at the red dots, which are Ameriflux, you see they're really funded by all sorts of different funding agencies, driven by individual site-specific research activities that are funded by small grants. And then a number of core Ameriflux sites are directly funded by DOE. And then there's support from the Ameriflux management team in terms of data processing and quality control and so on. But if you look at the distribution of the site, you see the advantage of really having a dense network because you're covering the whole climate space here, meaning air temperature, meaning precipitation. You see a really good coverage compared to the other sites. And then it's also important to know that even the neon sites are now part of Ameriflux, so even there is a cross interaction between these networks because everybody can basically contribute data to Ameriflux. And also important to know is that really the advantage is that there are quite a few sites in the Ameriflux network that have long-term observation time series that are even more than 10 years, and in some cases even more than 20 years. So if you go to an Ameriflux site, what kind of instrumentation and measurements can you expect? So as I mentioned earlier, we would have a sonic anemometer and then an infrared gas analyzer to measure water vapor and CO2 concentrations. And then if you look into the database, it's what you would expect, obviously net CO2 ecosystem exchange and surface and sensible latent heat flux. They are measured pretty much at all the sites. Then air temperature and humidity is also measured at all the sites. It's a fairly easy measurement and important both for calculation and interpretation of the fluxes. Then you see that net radiation is measured at almost all of the sites, so this is often used to calculate the surface energy balance closure. And then here, precipitation and saltwater content or water table depth are measurements of the important for the water cycle, and they're measured at many sites, but it's important to know that they're not standardized, so there are often issues with comparability of these measurements. And the Year of Water Fluxes at Ameriflux is really an initiative to improve these observational capacities that are relevant for the water cycle. And also this workshop is partly supported by the Year of Water Fluxes. Then you see even the components of for component radiation is measured at many sites, and then there is only a subset that measures methane ecosystem exchange. And then even less sites would have information about the partitioning of radiation into direct and diffuse radiation, and then you find only one site where saltwater potential or planetary boundary layer height is reported. So that is not to say that these kind of variables are not observed at the sites, but at least they haven't yet been contributed to the database. So now going to really the focus of this workshop is how can we link land and atmosphere observations to improve our understanding of land-atmosphere interactions. And if you look at studies that have been published over the past few years, you see that really there has been a lot of focus on land-atmosphere feedbacks, how they relate to drought development, heat waves, but also the carbon cycle, land carbon uptake, and ecosystem dynamics. So a lot of these studies, they relied heavily on modeling approaches, and really what would be really great to get out of this workshop is how can we improve our observational capabilities to really tackle these kind of questions also from an observational side. Now if you think about the land-atmosphere feedback as a coupled land-atmosphere system that really is driving both the climate and the ecosystem dynamics, we need to understand these complex feedbacks. And if you go to an eddy covariance flux tower, so you would have very good observation usually of soil moisture conditions, soil temperature, and then in the canopy, lots of measurements of surface conductance, of leaf area index, leaf water potential in some cases. And then we measure obviously the surface fluxes, in this case sensible heat flux and latent heat flux. And then we measure air temperature and humidity within the surface layer. So we have information about quite a few variables, and we can diagnose feedbacks between these processes. But what we're really missing out in most of these sites is that this upper part here, the diurnal growth of the boundary layer, that is related to entrainment of warm and dry air, but also the development of clouds and precipitation. And if you look at how these kind of processes feed back to what we're actually observing at the flux tower sites, you see that this is a coupled system that we can really only address if we measure across this whole continuum. And now I will go into a few topics that are relevant for flux tower sites, and I will focus mainly on the carbon cycle because this is really one of the main goals of the Ameriflux network. So it's really important to remember that there is a tight coupling between the carbon and the water cycle, and this is because the water cycle, and it's important for boundary layer dynamics because the water cycle is really tightly coupled to the boundary layer processes. So here in the canopy, when you look at where is the exchange of water vapor and CO2 happening, you zoom in, you see the leaf scale, and then on the leaves you have these stomata that are responsible for the exchange, for the intake of CO2 and the release of water vapor for photosynthesis. So now what happens if you have high soil moisture and or low vapor pressure deficit? The stomata will be wide open. There is no reason to conserve water. There is a lot of CO2 that can go into the leaf and a lot of water vapor that can get out of the leaf. So there will be high latent heat flux and a high photosynthesis. So now if the soil is drying, if soil moisture is decreasing or atmosphere is getting dry, water vapor pressure deficit will increase. Stomata will close. That will reduce the intake of CO2, but the plant is doing this to conserve the water, so to also reduce the loss of water vapor through the leaf. But it's not that easy because there is a coupling between the soil moisture and the vapor pressure deficit, and that is also facilitated through boundary layer processes. So really this is a feedback mechanism that includes important boundary layer dynamics. Now another topic would be related to the importance of diffuse and direct light for photosynthesis, for net CO2 uptake. So if you look at this study by Ricardo et al., where they show some observations from a broadleaf forest site in Germany. So you have light here, photosynthetic active radiation on the x-axis, and then gross primary productivity, so vegetation productivity on the y-axis. And then the pink lines are from a land surface model and the black lines are observations. And then you see for the same light intensity under direct light, the productivity will be much less than under diffuse light. So and that brings us to really the importance of understanding how direct and diffuse light is partitioned. And that is related really a lot to cloud development. So we really need to understand how clouds develop and how they feed back to the surface to understand photosynthesis. So now to think about this as a coupled system, we could look at the Bowen ratio to look at how much energy is partitioned to sensible and latent heat flux. That will impact how fast the boundary layer will grow. And then on the other side, we'll have humidity will determine also what the lifting condensation level is. So that's the level to which an air parcel has to be elevated for condensation to happen. So and when these two cross, so the air is mixed all the way up to the lifting condensation level, that's when you can have cloud development. And once these clouds develop, you will have impacts on the radiation balance. So these are all the yellow circles here, short wave, but also long wave radiation feeds back to net radiation and then to things like land surface temperatures, but also, as we've seen, diffuse and direct radiation, which is important for photosynthesis. Now, another topic that will be addressed in this workshop is aerosol dynamics. And aerosol dynamics, again, are quite important to understand the carbon cycle because they strongly affect diffuse radiation. So if you see here simulated impacts of biogenic secondary organic aerosols, you would see a small decrease in the total solar radiation at the surface. But what's more important is that we will shift quite drastically the partitioning towards diffuse solar radiation versus direct solar radiation. So that will have effects on primary productivity at the surface in ecosystems. Now, the vapor pressure deficit is another important topic, and how it relates back to water and carbon fluxes. And this has been the topic of many studies in recent years. And Kim Novick published in 2016 a paper where they looked at the importance of vapor pressure deficit for carbon and water fluxes. And what you see here is for one side where you see vapor pressure deficit on the x-axis, on the y-axis surface conductance, and then you see it's decreasing. So the more atmospheric water demand, the more the surface conductance will be lowered. But also the soil moisture plays an important role by modifying this response with soil moisture having lower surface conductance. So when we look at again what we mentioned earlier, it's the vapor pressure deficit is really a result of coupled processes. So we have surface fluxes that feed back to the boundary layer height to entrainment, which then affects humidity and temperature, and thus vapor pressure deficit, while they're at the same time directly also impacted by the surface fluxes. Now I will talk about the last topic, which will be about land use and management impacts on near-surface climate, and this has been the focus of many eddy covariance studies. But in a recent paper by Kim Novick and Gab Katul, they have been looking at how can we really make sure that we're getting robust results when we compare different land use strategies with eddy covariance flux towers. So what they've compared here is a flux tower above a forest site and then a flux tower above a grassland site. So that would be related to reforestation. And then if you look at the grassland side, so the measurement height is usually within the surface layer and well above the roughness sublayer. But in a high canopy forest, oftentimes you actually measure the air temperature within the roughness sublayer. And now if we would assume Monet-Nabokov similarity theory would be valid at this measurement height, and we would extrapolate the air temperature to the surface layer to compare these two sides, we would actually bias the air temperature at the forest side. So really what would help us in this case is to have a really high resolution measurement with height closer to this canopy to really see the actual profile and how it relates to the Monet-Nabokov similarity theory profile. And that will help us to really have more robust estimates of the impact of land use and management practices. So, and I hope there will be a lot of different topics that will be covered during this workshop. And what we really want to discuss is how can we enhance the capabilities of land atmosphere observation systems. There will be some focus on remote sensing, and then, but mainly how can we add or how can we use atmospheric boundary layer observations like microwave radiometers, LiDARs, radiosondes at flux tower sites, and how can we link that to an integrated observation system to advance our understanding of land-atmosphere interactions. And just recently, in a study published by Camilo Rey-Sanchez et al., they have been looking at combining wind profiler data with eddy covariance surface flux observations and atmospheric boundary layer modeling. They did this for a site in Tennessee and a site in California. And what you see here is in black the boundary layer growth across different seasons from the profiler, and then they use surface fluxes to force boundary layer growth models and compare how well they can actually replicate these boundary layer dynamics. And this was hopefully this can be done at many more sites. So really this workshop will focus on new emerging research questions, and it would be great if we could focus on things like what kind of variables and processes should we measure and observe at Ameriflux sites to enhance our understanding? Are there specific regions that are important? specific sites that could help us understand specific processes. Is there a need for long-term time series, for short time series? Can this be done on a campaign basis? And also, what are the logistical limitations to advancing this research? Is it cost prohibitive? Do we need a certain infrastructure? And then hopefully we can come up with new ideas about how to improve these measurements. Thanks a lot. I'm looking forward to an exciting workshop.